All right, we see the numbers climbing. Welcome, good morning, everyone. As the others join us swiftly, we expect and we anticipate having a fairly large turnout this morning as we deal with a very interesting topic, which is the issue of flooding that we are experiencing here in Jamaica, a fairly common phenomenon. And hopefully today we'll be able to explore some more of the challenges that we're experiencing and what may be causing that. So we know we won't be able to see the participants at this point. We can't see you, but we know you're going to see us as we're in a separate environment at this point in time. Yes, so thank you all for coming out on time and for joining us. We only have 1 hour to go between 11 and 12, and we want to make the best of that time. So thank you for being early. And as we await the others to join us, we just want to do some quick introductions and some housekeeping information. Now, as you noted very well, the topic for today is flooding in Port Maria, a hydrological perspective on this specific phenomenon. And our presenter will be Dr. Arpita Mandal, who is the senior lecturer at the University of West Indies in hydrology and engineering geology in the Department of Geography and Geology here at Mona. She's also an adjunct senior lecturer in engineering hydrology in the Department of Civil Engineering at UWI, and she's been teaching there since 2006 till present. She teaches water resource, hydrology, hydrological modeling, engineering hydrology, geophysics, and her main research focuses on hydrological modeling, climate change, and the impact of flood risk and water resources. So we couldn't have had a better person to walk us through this today. So she's worked on a number of projects locally, internationally, and regionally, and she's going to speak to us, as we said before, on the topic of flooding in Port Maria, a hydrological perspective on the phenomenon. But before she continues, we just want to mention a couple of housekeeping things. We're going to have the presentation first, and then you'll be given the chance to ask questions and have those questions answered. So if you look at the bottom of your screen, you will see a Q&A section. We're requesting that you type your questions in that section that we can have it collated for a later date. In case anybody forgets, they can type it in the chat still. But if you really want to verbalize that at the appropriate time, feel free to raise your hand. And when we get to the Q&A session, we will acknowledge you and you get a chance to ask your questions. All right, so hopefully that's clear for everyone at present. And now I want to hand over to Dr. Mandal, who's going to take you through the presentation. Oh, just for introduction, my name is Leighton Ellis. The civil division chair for the JIE as well. And we're going to have more exciting events. Another one comes up next week. You'll hear more about that at the end. Now over to you, Dr. Mandal.
Hi, good morning, everyone. Yeah, it's still morning. It's 11 o'clock. And thanks for inviting me to this webinar. It was it's very late where I am, but doesn't matter. It's online. We are in a virtual world, so zones doesn't matter. So yes, I'm going to be talking.
Dr. before you go on, I don't know if you mind. I don't think they can see you. I'm not seeing you, so I'm not sure if they're seeing you. Is your camera?
No, I did not turn my video.
Okay.
So do I have to turn it on all the time? I mean,
no, not all the time, but just so they can, know who they're speaking to.
Okay, no problem.
Yeah. All right.
Yeah. Okay. So, can everyone see my screen? That's important.
Yes, they are. They are.
Okay, great. So, this picture. So, I'm going to be talking on flooding in Port Maria, and you all must remember that Port Maria had another episode of flooding in February, early February, 3rd or 4th of February. There was heavy rainfall and the entire town got flooded out again. Now, those of you who have worked on hydrological problems in Jamaica and engineering problems know that Port Maria in St. Mary gets flooded often. It's a recurring issue, and it's the capital of St. Mary, and the entire town is located on the floodplain of the Outram River. The picture you see over here is from Hurricane Sandy in 2012. The picture was taken by one of the colleagues from WRA, and we got it from them. And the yellow building you see with the blue roof on top is the courts building. Then you have a series of business centers and not so much residential in this immediate spot, but it's a mixture. It's a very urbanized section, and it's at the mouth of the river, and the sea is on the other side. Of course, the sea is there, and so you have the backwater effect as well. Now, I started working on Port Maria we started in 2009 because of the MPhil research study of Anuradha Maharaj, who's there as a participant. So if you have any questions on some sections I'm going to show you, I mean, she's there to talk as well, because I'm going to show results of two work. One, the 2006 November flooding event, which was Ms. Maharaj's thesis, MPhil thesis, and then I'm going to talk on another recent study we did on multi-hazard risk assessments of 6 coastal towns in Jamaica by Smith Warner in collaboration with Smith. Well, it was led by Smith Warner, and I worked as a team member, and I'm going to show some results of it as well. Now, just an overview of flood hazards history for Jamaica. What are the main causes of flooding in Jamaica? Then going straight into flooding in Port Maria, possible causes, and modeling of the past flood events of Port Maria. Now, flooding is a natural phenomenon. And when we are looking on hazard and risk assessment, we have to be focusing on the hazard, which is the flood here, the flood depth and level of inundation, and the vulnerability, which is how, what are the exposures, what are the assets that are exposed in flooding. So in the previous picture, we saw the houses or the buildings, and the infrastructure, the roads. So those are the assets, and how vulnerable are people in the communities affected by flooding. Now, all of you are from Jamaica. I'm not sure if any of my peers from outside Jamaica are in the attendees list. I can't see it, but I shared the link. But just to give a context of where Jamaica is, it's located just below Cuba. It's the 3rd largest island in the Caribbean, directly in the path of the Atlantic hurricanes. And so we experience a lot of intense events in the months of September, October, November, and then in the early rain season in May and June. And if you look on the map on the right, that's the 30-year mean rainfall, annual rainfall map. And Port Maria is in the parish of St. Mary, which is the northeast part of the island. So it's in the medium rainfall zone, that's the green zone. The dark blue zone is the Blue Mountain zone, which is the zone of highest rainfall, and the lighter shades, that is brown, is the rain shadow area. Now, what are the main factors that cause flooding? And it's rainfall, distance from the stream, if you are looking at riverine flooding, bedrock geology, soil type, land cover, land elevation, steepness of the slope aspect, that is which way the slope is facing, which direction, flow accumulation, that is how much water is accumulating at a particular section of a road, if you're looking at stormwater modeling, or in a river section, and which way is the water moving. Now, this piece of figure which you see here is showing that in the time span from 95 to 2015, flooding accounts for 43% of the hazards across the world. So flood is one of the major hydromet hazards affecting globally and in the Caribbean and Jamaica as well. Now, to give you an overview of a flood hazard map, which we did in GIS base, this is showing the hazard rating. The darker colors, that is 0.80, are mainly the floodplains of the major river systems. Again, it is influenced by elevation, proximity to flood zone, characteristics of the soil, land cover, and precipitation. And here I have added 2 maps of Jamaica, one with the watersheds now and with the digital elevation model. Now, Port Maria and the Paji, if you look on the top map, it's just beside the Paji River. That's the Outram River. So that's where the study area is located. It's just at the corner of that bend over there in St. Mary. And here is the parish of St. Mary highlighted. It's in the northeast with a greater intensity of surface water drainage because of the geological properties. It's composed primarily of impermeable rocks, so you don't have a lot of groundwater over here. It's mostly surface water. Elevation of the island ranges from sea level to about 2263 meters, and rainfall, annual rainfall ranges from 692 to 6,900. Now, the flooding in Jamaica is characterized as depression flooding, especially in the limestone areas where water accumulates in the sinkholes and other depressions. And you also have groundwater-induced flooding, but majority of the flooding is riverine flooding, and that is in the brown section, which you see here. This brown stands for the Basal Activity. Just to keep it simple, the brown areas are the oldest rocks in Jamaica of Cretaceous age, that is 65 million years. And why do we call it an aquiclude? Because this is composed of non-porous, non-permeable. So if it's not porous, it cannot store water. And if it's not permeable, it cannot transmit water. So there is no potential for, there is very little potential for infiltration and thus groundwater storage. So you have more surface water runoff over here. And Port Maria is also a part of that basal aquiclude. Now, if you look at the compilation of all the meteorological phenomenon in Jamaica, right from as long as the record we could access, going up to 2021, we are seeing that there is an increase in flooding, and it's continuing till now. And along with flooding, you have landslides as well. The left figure is the compilation of data from 1850. There has been gaps in record because of some data we could not get. And then again, so you have a gap in 40s, 1930 to 40 in between. And then we have again a set of data. So this data is from a lot of sources: Green Archives, Met Office, OTPEM, WRA, all compiled together to see which months we have the high incidence of floods, which is mainly in the months of September, October, and then again in the months of May, which is the early rainy season. And we had published this in these two journals, and the next one is in progress, that is a vulnerability risk assessment. So in this map, in this graph, we are trying to isolate the different met events and trying to see what are the factors that cause the the meteorological factors, and most of them are, well, influenced from hurricanes and tropical storms. So just to give you pictures of some of the major hurricanes, which people in Jamaica are familiar with: Hurricane Gilbert, Ivan, Dean, all of which caused devastation in the island. Now, coming to flooding, the picture you see on your top left is those two are flooding in Kingston, in Harbor View, and very close to campus is the Kintyre. But these pictures are from the town center in Port Maria. The top one is from Hurricane Sandy in October 2012. This one is the bottom left one is Port Maria in November 2006, 23rd of November, and you can see how much of the town is under inundation. Now, this was not from any hurricane, because officially, although officially the hurricane season extends till the end of November, but we hardly get any hurricanes. This was from a cold front. And this is again the picture of Port Maria from looking downstream. And the river, as you see, has almost blended with the sea, is the Outram River. The coast's main store is the yellow one, and the Shell gas station is over here. That's all from Hurricane Sandy. Now, so here is a map showing the location of Port Maria in St. Mary and the northeast of the island. And the map over here on the left, top left, is the extent of the flood from November 2006. So it started all the way from the narrow channel, and water came down and spread over the flat area, which is at the mouth of the river. where the sea level, where the elevation is very close to sea level. And with water, the flood depth was almost 1.8 meters at the NWC pumping station. And on the right-hand side, you have another river, that's the Paji River. So it's a combination of two rivers which causes the flooding, the Paji and the Outram River. The Outram is running parallel to the road. That's the vertical one, which is coming down the orange line, orange shaded zone. So you have water level going from 0.3 meters upstream at the JPS office, right down to 1.8 meters at the mouth of the river. And if you look at the number of watersheds over here, Port Maria, this bigger watershed is this pink one is the Port Maria watershed, and it has two sub watershed units. One is the Outram and the other is the Paji. Now, as I mentioned, I have sections from two studies. One is the MPhil thesis of Anuradha Maharaj, that's analyzing high intensity rainfall driven river flooding in Port Maria. And based on some sections of that, we have a paper, and then I'm also showing the multi-hazard risk assessment study. Now, these pictures are from the November flooding. And if you look over here, the red line that is on the top left picture, that is where you see the new bridge, old bridge. This new bridge actually collapsed, and the picture over here on the right is the picture of the collapsed bridge. You can see on the one end of the bridge is almost the breakaway, and it's why? Because based on observations and interviews from the people over there after in 2009 when we went down there, the lower floorboard of the bridge was very low, and it almost touched the level of water when the flooding, when the water level, when the channel was completely filled with the excess runoff. So that is why it caused it to collapse, and also maybe it wasn't built properly. Now, this map over here shows the business centers and the different commercial activities. So this was mapped by a student, and when we're doing the field work. So if you see all the way from where flooding started, you have residential, there you have the fire brigade. So the river actually runs parallel to the road, but it's pretty much narrow in the upstream bend of it. And as you go higher up in the mountains, it's really not much visible. It's a narrow stream coming down. There's a sudden drop in elevation, and then it flattens out. So the gradient of the river changes very rapidly. It's steep, and then it opens up. So it's a kind of flash flooding over here. Now, all these businesses you see over here, the Shining Star, the trade, small to big businesses, all these shops and everything. If you look on the Google Earth image, these are all on the right-hand bank of the river. So the left bank does not have much infrastructures or any buildings. It's on the right hand, so the water water spills on the right hand side. It's an asymmetric channel based on some topography survey we had done over there. So this is the extent of the 2006 flooding. That's the light, that's the one in yellow. So if you look on the map over on the left, the one in yellow is the extent of the 2006 November flooding, and the blue one is the extent of the 2012 flooding. 2012 is Sandy, and 2006 is from the November front. So 2006 did not have much input from the Paji River, whereas in Sandy we had a lot of input. Now, if you look on the river channel, that's the blue line over here. Blue, for those who are new to hydrology, anything in blue stands for river. I know there are some attendees or students, maybe students here who are doing hydrology first time. So blue is always for river channel. So if you look into Google Earth, and you'll see very few development further upstream, and it is dense, it is full of vegetated, but the soil is loose. I mean, in simple words, it's unconsolidated, unconsolidated mud and clay. It's very loose soil. Much of it is weathered as well. I'll show you the geology map. Geologically, it's the Richmond Formation, but putting it in simple words, it's clay. Clay swells a lot, takes in water a lot. It does not allow water to percolate, so all the water runs off. So you see you have a combination of different tributaries coming down, and they meet at a point. If you focus clearly, if you focus deeply into the into this blue line, the network, the dendritic drainage system, you'll see three tributaries coming down, and they are joining at one point, and from there is flowing down as one single channel. So all the water coming from these three tributaries will culminate at this point, at the junction, and whatever accumulates from there flows straight through the river and spills over and spreads on the eastern side, on the right-hand side. And that's the floodplain where the flooding happened. And this is again the Outram and Taji. This map is from WRA showing the extent of the flooding. Now, these are some pictures of the recent flooding that happened, and this is exactly what we heard from the residents over there, that there was a lot of sand and silt and which affected their houses, affected their shops. The courts building is still flooded out, same level. This is the February flooding. Now, this one is interesting because these pictures were taken when Ms. Maharaj was doing her MPhil work. So it's 2011 picture, but you see on a dry day. Okay, on a dry day, we went for flow monitoring with a handheld flow meter. And if you look at the condition of the river, it's turbid because of the basement rocks being clay and shale and slow bank erosion adding to the siltation. But look at the amount of garbage that broke these trees and all these branches in the river. And this is not very far from the mouth of the river. We could not go further upstream. We had to go in a boat. If you see her, she's sitting there. We could not go further up because the river was in this state. Now, I personally think that this could also add to the blockage of the drains as well, because if all this, and there's a lot of garbage which come down from the shops and stuff which are on the bank of the river. People just throw things into the river and the drains are not clean. And we know that this is a recurring thing. Only when there is a hurricane alert, drains do get cleaned up, but otherwise it doesn't. So all those things adds up to block the natural flow of the river. And when your channel is already blocked up, you have less space for the water to accumulate. So it spills up and breaks the banks. On a dry day, if you look here, the water level is very low. You can imagine what force is coming down and it caused flooding, because this is on a dry day at the mouth of the river. Now, some interviews from the people in the area, this part of a thesis. Most people said that it was 1 to 2 meters of flooding in 2006 and 12. And according to the local residents, drainage maintenance is one of the major causes that is causing flooding in the area. Now, just a brief overview of the geology. Port Maria is located in this backwater belt in the Creek area, and it's mainly composed of volcanics, volcanoclastics, granodiorites, again belonging to the basal aquiclude, non-porous, non-permeable rocks, which allow more surface runoff. So we did some riverine flood modeling, hydrological modeling to create a flood map and assess the flows and simulate what was the amount of water that came down from the 2006 flooding. That was done in 2014, part of the thesis. And then we did again in 2021 from the JIE CIVIL project. That was looking at the 50 and 100-year flows. So hydrological modeling was done in HEC-HMS. It involves this suite of tools, which is using the DEM, then you're running it through a series of ArcGIS steps to get the drainage network, then finding out the length of the channel, then putting it in HEC-HMS, where you create your basin model or the watershed model, which is pretty much showing how many catchments are there, and then you add your rainfall data and run the simulation, and the outputs are discharge hydrograph. Now, why do you need to do a hydrological model in this case? Because although the area is being repeatedly flooded out, this river is not gauged. There is no stream gauge network, stream gauge station in the Outram and in the Paji River. So you don't know what is the amount of discharge that happened from several flooding events. So when you don't know these, when you have these unknown variables, you have to do some modeling to simulate past events so that you can prepare that, okay, in 2006, this was the level of water, in 2012, and if the 50-year, 100-year floods are, what is the volume of water in the channel, then you can design infrastructures, then comes the next engineering can be done based on it, rather than going on an unknown, completely unknown field. So that is why hydrological modeling was carried out to simulate the 2006 event, because that was the first major event, one of the recent major, I should say, which caused the damage in the area. So this is a simple flow chart showing how it flows. So you create your base watershed model in GIS, and then you run it through HEC-HMS, where you add your rainfall data as the MET model. Then you control simulation, means you control specifications, you adjust how long you want to run the simulation. So you enter the rainfall data for that particular time period, and then you get the discharge hydrographs. Now this one you're seeing now is the JIE project, where we looked at the entire Port Maria watershed. So the river on the left one, the drainage network you see on the left, extreme left of the color-coded figure over here, that's the digital elevation model or the topographic model showing the elevation of the area. So you see it has ranges from 507 meters upstream to going down to sea level. So the left one is the Outram River, and the right, the river channel on the right is the Paji River. They don't meet at any point, at a particular point, but they both contribute to flood out the flat area. These red points are drainage points, which is basically junctions of two tributaries. So drainage points in essence means junctions of two stream networks. And on the right, you have the, I'm showing you some blue lines, which are section lines. So survey was done in this project, meaning topographic survey to get channel cross-section data, because I'll touch on that later on. One of the challenges in hydrological modeling is the irregularities in the DEM available for the island, because there are a lot of gaps in the DEM, in the digital elevation model. And the resolution is not very fine or high level to do modeling on a small scale. So you will see gaps in data, meaning you have elevation at 2 meters, and then there is a sudden drop and elevation drops to 1 meter. But so when the elevation is dropping by 1 meter, the model is telling that the water will fall by 1 meter. Whereas in reality, when you take your survey equipment and go in the field, you will see that the point on the DEM where the elevation comes as 2 meter, in the field, it may be 1.5 or 1.2 meter. And as an engineer and as a scientist, you know that this is a big difference in the elevation. So that is why we are always stressing on collecting high-level survey data. And so these survey data was collected by a surveyor, and that was then fed into the original DEM we had. And a new DEM was created both for this project and in the 2006 study, so that we can get as best as we could the channel cross-sections at the mouth of the river, especially for flat areas, because even a small variation in elevation can cause error in overestimate or underestimate your flow. So when I'm talking about basin model, so you start with the elevation model, you run through a series of steps, not going into the technicalities, and you get these polygons, which are the catchments. Why is this important? Because the area of the catchment is important, because velocity, flow, discharge is simple formula is velocity multiplied by area. What is the area of a catchment in which one tributary is? So that area contributes to the amount of water. In hydrology, I mean, these are some basic things in hydrology. Q is velocity multiplied by area. So you need the area of the project area, the area of the catchment you are working with. So when you get this black and white diagram with the blue lines and the dots coming in, so you know where your catchment is. how many catchments are contributing to the flow at a specific point, and then you can get your model running accurately. So once you plug all these things in HMS, basically, we have to find out what is our point of interest. So flood modeling points of interest. Points of interest are not exactly where the junctions are. It's basically sections which are upstream of the flood area. So let's see some chat messages. Yes, I did the return period. Sorry, yeah, I'm going to show it. So those are the points where we are going to try to see what is the volume of water that is coming out at those points, okay, from the model. Because throughout the area, there's no stream gauge network, so you don't know what is the discharge in the river. So that is why we are doing hydrological modeling. And so going in the field, the team selected a set of points which would help in creating the flood map. That is the yellow points which are upstream of important locations. Now, this is basic equation which is based on the soil conservation system surface runoff, and it uses CN, which is a runoff coefficient, which is coming from the soil and land use. So you get the soil map of the area, you get the land use data, you overlay, and you assign some empirical numbers, which is basically ranging from 0 to 100, with higher numbers meaning less infiltration and more surface runoff. All right, so let us look what was the runoff, what is the rainfall. So this is the map for the 2006 event, and we see the rain gauge stations in the area are this ones in square, that is Port Maria, Brimmer Hall, Hampstead, and we use another one of Albany. The rainfall that was recorded in Port Maria was 240 millimeters, which is in 2006, and Brimmer Hall was 332, which was close to the 25 and 50-year rainfall runoff, rainfall return period. So if you look on the table over here, daily rainfall data for the stations were collected for 1994 to 2019. Why 94? Because before that we did not get, Met Office doesn't have data before 94. So the data wasn't very wasn't good at all. So that's the time period we got, and from that, once you use your statistical methods to get the rainfall return period, you can see here the 25-year rainfall return period from this data set for Port Maria Station is 241, and the rainfall for 2006 is 240. So it was a 25-year rainfall, whereas for Brimmer Hall, it all was 25-year rainfall, the 2006 event, and same for the 2012 event. So this was done in last year. We updated it because your NWA's drainage guideline has data up to 2013. So we updated it, including the last 5 years. Now, so these rainfall data you see over here were used in the hydrological modeling. Now there's a method of downscaling the 24-hour rainfall to hourly level by a standard model. So we downscaled it into hourly data. And so these graphs you see over here, this is the data we use to feed into our MET model. And once we got that, we run the hydrological modeling, HMS, and this is the flow these are the different flows we got at different points of interest. So the green points of interest are based on which is important for water, for flood assessment and for engineering. So all those points you see, CO2, CO1, these are at the mouth, absolutely at the mouth. OR1 is also at the mouth of the river, which is the highest flow, approximately 700 cubic meters per second for a 100-year event. And the extreme left, on the left one, if you see OR9 and 8, these are the upstream ones. So flow is always less and upstream because you have less contributing area, and when it's coming down, more and more catchments. You saw my figure earlier of more catchments and the drainage network. So more catchments are contributing to the flow downstream. So water is coming from all over the place, and put in simple layman words. So water is coming from the side areas, the catchments, the different tributaries. So as you move downstream, your volume of water increases and time to peak does not change, also goes, also reduces. So the maximum was 700 for a 100-year event. So a 100-year peak, sorry, a 593 was simulated for OR1, not 700, was not clear. While PG1 corresponds to the mouth of the Paji River. So Paji is on all the letters you see with PG stands for Paji, and OR is outram. So Paji will recorded a peak of much higher, 1037 cubic meters. This is a 100-year event. And these are some of the other points of interest, which is along the main channel, upstream of the bridge, upstream of the town center, in between the town, near a culvert. So all those things were noted based on where infrastructures are. So once you see flowing downstream, they are joined by tributaries. So as if you have more tributaries coming in at that junction, you will have a higher volume of water. The last critical junction is at OR3. OR3, if we go back, is at the point where the upstream tributaries combine and the water flows down as a single channel. Now this section is not done by me, it was done by Daniel Dowding from Smith Warner. So she used the hydrological modeling data and the DEM to run the hydraulic in Mite, see the flood map. And this is what we got in the project, that is the extent of the flood map and inundation depths. And then we tried to correlate with the WRA's water level, almost similar values we got, because you have 1.2 recorded for the 2006 and 12 event, and then Mike 21 modeled it 1.16. So there was pretty much good correlation, 1.2 near the housing scheme and 1.44 from the model. Now, so the hydraulic model used all these flow data into the hydraulic model to get the final floodplain map. So that was the study that we did last year for the 5-year, 25, 50, 100-year flows for Port Maria and Outram River at specific points of interest. And then this is some specific, the 2006 event. So similar approach, but in this case, Ms. Maharaj modeled just the section of the mouth of the river where the 2006 flooding happened. So we are dealing with a much smaller number of catchments. So again, on the left, you have the DEM where the survey data was coupled with the existing DEM, modified, cleaned, run through the GIS steps to get the number of polygons or the catchments. And you see here, we still have the same, quite a bit of catchments, but we have less catchments because we are not going further upstream of the entire study area. So we are limiting ourselves to just a few catchments upstream. So if you look here, the blue is the extent, and the last junction, or the last, the river just join, the different tributaries meet at a point upstream of this blue area, and from there it flows down. So the overall, the network is the same as the previous one, because of course it's the same river. So if you look over here, these symbols stand for reaches. Reach stands for the section of the channel, and the junction is where the rivers are connected. So all the water that is coming down upstream flows into reach 4. That is just, reach 4 is just a terminology because you started labeling from the top as 1, 2, 3 different segments. So from this section marked as reach 4, water moves down straight into the channel. There is no bifurcation. It's a straight channel running down. No more tributaries coming in. And the flow over there, which we modeled, was approximately 200 cubic meters per second for the 2006 event. Then this one is showing the different flows for the different reaches, reach 4, 5, 6. And you will see reach 6, which is the last end of the last segment of the river at the mouth. The flow, the peak flow is approximately 183 cubic meters for the 240 millimeters of rainfall. So this is all we had been doing with Port Maria and possible causes of flooding. I would say the high intensity rainfall for a short duration of time, and it's almost equal to the 25-year period. Steep topography and asymmetricity of the channel. There is extensive urbanization near the mouth of the river, where the elevation is near sea level. Poor maintenance, and if you're going in the field in a dry day or in a wet day, you will see it straight away. Much of the mouth of the river, even the drains at the mouth, are clogged up with garbage, and some sections of the river is full with trees and broken branches and stuff, so which is blocking the flow. One of the suggestions we suggested was installation of a discharge gauge at the Outram River, which will help to monitor the flow and issue flood warning, which is very important because this town floods a lot. So there should be a flood warning or something over there to make people aware that, okay, X volume of water, X time to reach peak flow. This should be, you should evacuate well, if possible. And a few years ago, I had read an article in the newspaper where there was discussion of relocating the town, but I don't think that is feasible. I'm not sure about that because seriously, it's a lot of business centers over there. So to move the entire town to a new place, I don't know how economically it's feasible. So that is all about what I did and what we did, me and before me, Ms. Maharaj did for her MPhil. So that's what I tried to present. All right, thank you. And
thank you very much, Dr. Mandal. Please grab a drink of water in the meantime while we fetch some of these questions that are there. So very exciting, very interesting presentation, very detailed as well. And so I'm sure all of us here would have learned something so far. We do have a few questions posted in the chat. One of them I think you addressed earlier, which was from engineer Miles Harris, asking the question, how did you calculate the return period for the 2006 or 2012 period? And I believe you had answered that, but you can feel free to touch back on that one again when you come back. We see two other questions coming in. One from, a couple of questions are here. So let's just jump in for what Maurice Jones is saying here. For such a history of flooding, is there no intensity recording rain gauge network in the area to properly characterize the temporal and spatial distribution of impacting storms? I think you touched on that, but you can still express that once again, just for the benefit of recording the responses to the questions.
There is no AWS. As far as I know, there's no automated weather station over here. There is only, the rain gauge is only recording daily data, and that is also one of the limitations because the data I'm getting from Met Office or from the gauge is accumulated daily rainfall, so 240 millimeter of rainfall at 24 hours. But to do, or to set up for early warning system in response to Dr. Smith's question on the top, and also to answer, you would need weather stations which give you hourly data because we don't know when that peak rainfall happened. We are downscaling it by a statistical type 2 rainfall distribution, which is widely used in Jamaica by engineers and hydrologists, but that is a synthetic estimation. So no, there's no stream gauge. The rain gauge is 24 hours, so no intensity data.
But given the second answer that is coming up to his question, would you not say that the so installing an intensity gauge attached to an internet assistant would that assist in the warning? So is it that internet access may be a part of the problem in that area, that if that were there or available, would that aid in any way in giving us some early warning in the system?
I don't know about the internet part for Shibir. I'm sure there will be there is internet with the town center, but you have to, well, they have to put up an AWS, or automated weather station for recording rainfall at hourly, and also the river has to be gauged. So that stream gauge has to be set up in the river. Otherwise, water systems don't work.
Right, right.
So like you have in Rio Cobre and Rio Grande, which you don't have in many like the flood warning system. But even if you don't have a flood warning system, you have to have a basic stream gauge station like the one you have in Hope River because if you do not model, you don't know what is the volume of water in for that event, pretty much, because there's nobody measuring the flow at that time when the flood happened.
Yes,
Unlike
yeah.
the many rivers in Jamaica are monitored, but many are not. So this is one of the not, which is a major now because of the flooding.
Yes, and given the recurrence of such an event, we were 2006, we had the 2012, and now 2022. Clearly, there is still a major gap in this space. The fact that we have such a recurring event, it clearly means that there's some expediency need to be attacked in addressing this specific issue in this case as well. So Dr. Smith had posted in the chat, just to follow up, could we use this for an EWS he's referring to? So he had posted some image of how mobile phone towers could help monitor rainfall in developing countries. Is that something that you think that's a possibility?
Yeah, but talking to people over there now, my experience in Jamaica is less than you guys, but talking to people over there, they say that after the highway came up, this flooding has started happening. So I don't know if that's the main reason, because the local people tell that there wasn't so much flooding before. So once this new north-south highway and the road came up, it started. But
so there's a possibility that the study that may have been done for that highway wasn't expansive enough to consider this as a possible effect based on the anecdotal data we're getting from the citizens. Would you say that?
Sorry?
Meaning that based on what the residents are saying, again, it's anecdotal. They're just looking at a cause and effect from their perspective, but it's still important. And they're saying that prior to the highway, this was never as severe. Now, what we're also saying is, could it be that the analysis done in the highway project wasn't as extensive to look at the effects that may have expanded towards this town in particular? Would that be something you could speculate as well?
Could be. I did not see that report, so I would not be able to comment on it, but it could be.
Okay. Again, so that's something to study, right? That would be something to investigate further.
Yes. Yeah.
All right. All right. So we have another question here from Miles. Before we go to the chat, we see Miles here. Is there any data on the recent flood that gives an idea of the return period? Again, looking back at the 2022 model rain event he's referring to last month.
I did not get that data yet. So once you get the data, you can compare it. I did not ask Met Office yet for the data.
Right. So it may be there, but you don't have it in your possession at present.
Yes.
All right. So that's something for us to investigate further as well. All right. So we still have a few other questions in the chat. I think did we touch on Maurice's question? Maurice Jones had a question.
No.
All right, so let's touch back on that one. For such a history of flooding, is there no intensity recording rain gauge network in the area to properly characterize? We touched on that one, right? Yes.
Yeah.
All right, so the next question from Chase Stewart says, has there been any calibration and validation work done for this model? Yes,
I showed you the calibration. Yes, the one which I showed, the first few slides I showed on the entire Port Maria one. The hydrological model wasn't calibrated, but because you don't have observed flow data to calibrate it, but the hydrological model generated outputs, that's the hydrographs, which were used to create the hydraulic model, has been calibrated. And that is these slides over here, where if you see the difference between the observed flood depth in the field by WRA 1.2 and the model 1.16. So that is the calibration. You can see there's not much difference. Now with the 2006 event, which was the study of Miss Maharaj, who is MPhil thesis, she did the hydrological modeling part. Again, because of absence of stream gauge, there was not direct calibration with the stream gauge, but yes, sensitivity tests were run with the CN number and Monte Carlo simulation. So some amount of calibration was also done on that work. But absence of gauge data limits this this high-level calibration work for sure.
Okay.
That is why you need to have a gauge over there.
All right. So we still have some questions here from Miss Mirage herself. So she's saying, thanks again for the presentation and the comprehensive approach that you have taken. Now, one of the questions she's asking, has the new bridge, remember there are two bridges you highlighted, the new bridge with the low flow board been removed? Question one. Follow-up to that is, has there been any input or interest from ODPEM and or the Parish Council of St. Mary on the work done towards possibly arriving at a solution?
Ms. Maharaj knows the answer to these questions.
Well, I think she's just making it general, so everyone would benefit.
I know why. I mean, well, and rather maybe if you're still there, you know the answer to the second part of the question. Being very, I don't know how to say, no, there has not been much improvement in the area. Interest input from ODPEM, I will not go around that. It'd be very tricky to say, yes, there may be interest. We did share your thesis and there was presentations and stuff, but I don't see any improvement or any new thing happening since these studies have been circulated and presented to stakeholders. Honestly speaking, I did not see any. Yes, there is an interest. People are asking questions. What do you suggest? And what is the data? And share the slides, etc. But in terms of something tangible or concrete coming up to prevent the flooding, no, there hasn't been anything done there. The new bridge, no, yes, it has been removed. There's no bridge there.
Okay. All right.
But
so
as for the Parish Council, no, I did not see. Ms. Maharaj herself had presented this, her initial day, she had presented her work to the mayor of the St. Mary Parish Council, along with ODPEM and disaster coordinators. So they are aware, and it's not a new thing, it's happening. But as I said, it keeps happening. There hasn't been any.
Maybe they need a little bit more nudging, and so we at JIE will see what assistance we can lend to your study and otherwise.
Try to set up a gauge over there if you can with JIE and WRA. Set up a gauge.
Yeah, exactly. That the least that we could do is probably have some more recording done. Another point here mentioned by Dr. Smith is the rainfall attenuates cell signals, and cell towers can be used to measure rainfall very accurately and in real time. So that's, I guess, something that he's looking at as well in his studies. Yeah. And I guess you can affirm that.
Mm-hmm. That's nice.
All right. So we also have another question here where someone is asking about the presentation, if it can be shared. So we will look at sharing that afterwards. Another question from Zachary Free is, or Zachary, how can you, okay, same thing again, a copy, everybody wants that. So Maurice Jones, on the matter of stream gauging, they would have to be located at the points where the water is in the channel, and after JPS, which is upstream, much of the water left in the outram channel. So we would need appropriate located gauges on the tributaries themselves. So it clearly means that a number of them are needed in that case as well. Another thing that popped up was the whole necessity of, is there any way maybe detention pond or retention ponds may be able to assist in reducing that flooding effect downstream? Is there any possibility for that?
Well, when based on field visit, and if you go there, it's the river is from the JPS, I mean, after you, from the JPS location, it's pretty much straight. And one side is, you have the road, the proper concrete paved road on one side, and the other side is hills and bush and all those things. It's steep. So we didn't see anything, I don't know, but it's just one channel going down parallel to the road. So I didn't see any place where you could put a pond.
Okay. Okay. All right. So then that's not a likely possibility. So we're just looking at different ideas that could be explored to minimize the effect. For anyone else who have any questions, feel free to raise your hands. You can voice them if you need to. But I'm not seeing any more questions in the chat that we have not addressed.
Another, you would like to say something on your experience, if you remember, on the river channel, and I mean, maybe she can.
She can, if she can, if she wants to, she can. I see some anonymous attendee. Oh, you saw that one. Okay, so you're answering that question. So go again.
There was the contribution of storm surge in Sandy assessed? No, we didn't do storm surge.
Okay. All right, so that was not addressed. Other question from Michael in the Philippines. Michael, welcome. Thank you for joining us from so far. The e-certificate, we're going to look into that one. There may be some possibility. It's an hour-long event, but there may be a possibility for a CPD, which is, I'm sure is what you're referring to, for your professional development requirements in your various professional bodies. So we'll look into that as well. What we have your data, I'm sure, from the registration, and we will look to send out that information as well. So thanks for that question. If there are no further questions or comments, we just want to thank you again, Dr. Mandal. I know you're very far away. Most persons probably thinking you're right near to us, but you're very far away.
That's fine. It's 30 p.m. here. That's okay.
Yes,
it's online.
Okay, great. And the time zone is very different, but we're glad that you're able to assist us in giving us this webinar today and sharing the knowledge and the experience that you have garnered with your team at the university, as well as at other private and public entities around, and making us more aware as to the challenge we're experiencing in St. Mary, but that could be generalized across to other sectors we have in Jamaica, and a clearer understanding of this phenomenon called flooding and how we may be able to address it if we just change the narrative a little bit more. Upcoming or next event, we just want to mention that at this point in time, next week, Thursday, the 10th of March, we should have a presentation by Dr. David Smith from the Smith Warner International, the Director of Quality and Innovation, and he'll be speaking to us on the topic COP26 and Caribbean engineering, its impact on policy, practice, research, and education. He was one of the persons privileged to have attended the event last year, November, I believe it was, and would have garnered a number of insights from that side, and is now willing to share that information with us so we can know what direction we're going to move in as we prepare for engineering, not just today, yesterday, but of course the future, which is where we want to go to. And our theme for this year at JIE is focusing on resilience and the future of our nation as well. And so these presentations are geared towards assisting us in that regard. So thank you all for your time. Please enjoy your lunch when you have it, and we will see you again in the near future. Do you want to share your email with others, Dr. Mandal? I don't know if that's something you're interested in doing.
Yeah, I can share. I mean, it's
okay. So we'll share the email. Yeah. Go ahead. Do we post in the chat?
Yeah. Yeah. Okay. It's small a.
Oh, okay. I see. Okay, you just shared it. Okay, so that's a small a.
Yeah. Yeah.
So it's arpita.mandal@uemona.edu.jm. Feel free to reach out to her if you need any further questions, queries, or maybe even interest in further research in the area as well. She'll be happy to assist in that regard. So thank you all again for coming out, and please enjoy the rest of your day until we meet again next week, Thursday, for our second event led by Dr. Smith. Enjoy the rest of the day.
Thank you, JIE, and thank you, Ellis.
Thank you.